Kita चाहिए अपना So I want to talk about zero-free regions of L functions today. So you know, I don't know, do you know zero-free regions of Riemann zeta functions? Yes, zero-free region. Okay, so I mean, what is really the difference between an L function that is not a Riemann zeta function? Is that there are these characters, yeah? And so you saw yesterday that we have things which are modulus some q. And so the zeros, essentially, the result for zero-free region of Riemann zeta function is essentially the same, but with a difference, and that's what I will talk about. So this is zero-free regions, yeah? So this is, so for Riemann zeta function, we know that there exists a positive, there exists an absolute positive constant C such that zeta of S does not vanish in a certain region which depends on C for sigma which is greater than 1 minus C by log tau I thought the theorem was false. No, it's not. That's not what you are discussing. Okay. So, yeah, these constants, what do you mean by an absolute constant? It means that the constant does not depend on any parameters, okay? there exists. Yeah, and some computational work is done sometimes to find this C. Okay, how good this up to which C we could say something. And if we have the Dirichlet L function, we have a corresponding result, and the corresponding result, you can imagine, is going to need a Q. It's not going to be independent of the Q. Yeah. So this is the result for L functions. And here by L functions, I mean the kind of L functions we introduced yesterday. These are Dirichlet L functions modulo Q. So there exists an absolute positive constant. I'll still call it C, okay? Unless it's being used in the same theorem several times, we keep our C as C, okay? I mean, there are authors who have, whose books you find C17 and C25 and so on. It's quite confusing. The one by Bombieri, for example, yeah? So Bombieri's book on this similar things, it has every C is different to make sure that he is not talking about the same C. Okay, first this, but we won't do that. Yeah, there exists positive constant C such that if chi is a Dirichlet L function, and then a Dirichlet L function must have a Q modulo with character modulo Q, then the region, which region will it be? I write R for the region. This depends on Q. This is the set of all S such that sigma is greater than 1 minus C. And what do you expect here? Log, there should be a Q that appears, Q T plus 2 for sigma between 0 and C. In this region, so then the region, this region contains no 0 of LS chi, almost. This is almost true. There can be an exception, okay? Unless what happens, chi is a character, is a quadratic character. Yesterday, I introduced this idea of quadratic characters. Quadratic character, in which case L S chi has at most 1, 0. Okay, so the only exception that can happen is in this case where chi is a quadratic character. Okay, And if the zero does exist, it is real in R Q. So we should understand what this statement is, that if Q were 1, we would come back to this theorem, yeah? And then, of course, there would be no such case that you had quadratic character modulo Q, and the second part would not exist. So this is the second part that is different from the Riemann zeta case. And this zero, if it exists, okay, it is called the Siegel zero, okay? Or sometimes some people call it the Landau-Siegel zero. Ivanich, for example, says that Landau has to be named. Or if you don't want to fight, you call it the exceptional zero, okay? So, so let's, now that tells us that if such a zero exists, so if, that's the end of the statement, yeah? Definition, if a zero, as in the theorem, exists, it is called the exceptional zero or the Siegel zero or the Landau-Siegel zero. Okay. Now, what is the statement of the Riemann hypothesis? You remember the statement of the Riemann hypothesis? Yes, what was it? Yeah. So, what would you expect for the L functions? What would you expect for the L functions? So the Riemann zeta function is one of the cases of that. So in general, you would expect that that's also a hypothesis which is completely open. It's called the generalized Riemann hypothesis. Some people also call it the grand Riemann hypothesis. In any case, it's GRH. So this says that for all L functions, the non-trivial zeros would lie on the line s equal to half. All right. So now there is a question. Do you think, do you like the, would you wish the Siegel zero to exist? If you were given a wish, would you like the Siegel zero to exist? What would happen if a Siegel zero existed? What would happen? Yeah, what would happen? Then that means that there are zeros, non-trivial zeros whose real part is not half. Yeah. So this is a bad zero. Yeah, it's a bad zero. But what is also bad about it is that after all these years, I mean, you see, this is from the time of Landau and Siegel, we still haven't been able to throw it out. Yeah. If you throw it out, it does not mean that the generalized Riemann hypothesis is true, but it comforts the generalized Riemann hypothesis. If you get one, it's really bad because it means that the hypothesis is false. Yeah. So these Ziegel zeros are important. Yeah. And a lot of work goes on in this area. Nobody has yet either found one or proved that they don't exist. Yeah. So so their existence, the existence of Ziegel zeros would prove the generalized Riemann hypothesis to be false. Yeah. So it probably doesn't exist. Between you and me, I think it doesn't exist. So we don't have a proof. So the proof of this theorem is long and somewhat technical. I will not do all the details because also the proof is very similar to the proof of the Riemann zeta function. I will concentrate on this part of the proof. I mean, we could do the first part in the exercise as an exercise in the second half, and but the second part, the one that is where the L function, the zero free region of the L function is different from that of the Riemann zeta function, is here, unless chi is a quadratic character, in which case it might have one. So I want to give you an idea of the proof. I will not do every step in detail, and you can do some of the steps yourself. However, I will tell you how the proof runs. Yeah. So we will divide the proof into a certain number of cases. The first case which we will take is proof of the theorem is when chi is complex. So what happens when chi is complex? I mean, we saw a proof yesterday where we divided the proof into several parts. So proof okay. So so the cases are when chi is complex and when chi is quadratic. Okay. When chi is complex, the proof is not very different from the proof of the Riemann zeta function. I will leave it as an exercise, which we, if all goes well, we'll do together. Okay, if all doesn't go well, well, you have a long life. You can prove it yourself. So So, yeah. So let us move to the case where chi is quadratic. Okay. So case 2, when let chi be quadratic. If chi is quadratic, then chi square is equal to chi 0. Okay. Okay. So just just a comment that I want to make about chi being complex is that this does not happen. Yeah. If chi is complex, then chi square is not equal to chi 0, and therefore these terms will actually show up. The chi square terms will show up, and here chi square term and it shows up. It's simply chi 0, and then it doesn't do anything. So we begin with an observation that you remember we saw this. I mean, maybe we didn't see it exactly like that, but we saw that if I take the logarithmic derivative of the L function at chi 0 and divide it by Ls chi 0, and if I do the same thing for zeta, then the difference between this, the absolute value, is less than equal to log of q for sigma greater than 1. Okay. Now, if I do this, then I can use a result for the real part of zeta prime by zeta, which we did, which you probably remember. You saw this. So what do you know? You know that this, the real part of zeta prime, s by zeta of s, this, what is it bounded by? Does anybody remember? So yeah, so let's put a negative here. So this is, you remember this formula, real part of 1 upon s minus 1 plus some constant, and this time I'm using a C1, okay, because I have the several constants in the same proof. Yeah. So C1 log tau plus 2, okay. And now we will use the part that zeta square is equal to, chi square is equal to chi 0. Yeah. So if then, and bring it back onto this result. So from there, because of, if chi square is chi 0, then you put it back over there and you get minus the real part of L prime sigma plus 2i tau chi square instead of chi 0, okay, by L sigma plus 2i tau chi square. The real part of this is going to be less than the real part of, I write that out, 1 minus 1 upon, so sigma minus 1 minus 2I tau plus, and now I'm using another constant, C2, because I have a C1 over there, log of Q T plus 2. Have I got my tau? Okay. Yeah. Okay. C1, C2, etc. are constants. Okay. Now I'm going to choose a sigma. All right. So choose a sigma. It's 1 plus, the sigma is greater than 1, delta upon log, this log, which I have, q tau plus 2. All right. And I will let gamma be greater than sigma upon this, okay, log q. All right. And if you simplify this, please do it, because I didn't do all the details of the simplification. I get that we get beta. What was my goal? To get 1 minus, so C3, I get some other constant, C3 delta. Don't worry about the 16 over here, it's just on some simplification. I'll do one of the simplification once so that you see how you do it. There's no mystery in it. And delta upon log Q absolute value of T plus 2. Okay, so what did I need here? I needed here that gamma was greater than delta upon, was greater than something. Okay, so if this happens, even if I have a quadratic character, then things are not, I'm still within the good strip. All right. Now, when will things start getting beta and gamma are the zeros of LS chi. I mean, the real and the imaginary parts of sorry. Okay, real and the imaginary parts. Now come to the case where you have gamma to be less than delta upon log q tau plus 2. Okay. So this is going to be the third case. well, whether it's a third case or not. It is a third case in the case, I mean, it is a subcase if chi-square is chi-0, then I divide it into two cases. One is this one, the other one is the other one, where gamma is less than. So gamma is small, okay? So let's go to the last case. And this is the one we will do in more detail now. And the other one we will do in the as an exercise. So now we let tau to be less than delta by log Q. Okay. What was my claim? My claim was that I'm going to have at most one real zero, right? So to um, to prove this claim, what we will do is we will take two zeros, and I will begin by taking two complex zeros and show that there is a contradiction. Okay, so you, instead of taking two complex zeros, you can also take two real zeros which are different, or two real zeros which are the same repeated. The argument is the same. Okay, so it's gamma, yeah. So we assume that there are two zeros which are complex. Okay, the same argument in the region. Okay, the same argument would go through for two real zeros, distinct or repeated. Okay, so we will only do it for this case. So now, what happens when I have complex zeros? If I have complex zeros, what you have the complex conjugates, yeah? So, so now we notice what I did before, L prime sigma chi by L sigma chi. This is less than C1 log Q minus a sum over the zeros, 1 upon sigma minus rho. Yeah, rho being a zero. So rho runs over all the zeros. Sigma is real part. Okay. Now, the sum over the zeros, this is going to be real. Why? Because these rows, they occur in complex. These are complex zeros, and they occur in pairs of complex conjugates. Okay, I can write it. The sum of zeros is real. Sum over zeros is real since they occur, since zeros occur in pairs of complex conjugates. All right. Okay. Now, so complex conjugate means I have beta plus IY and beta minus IY. And they're really complex, means they're not real. So I'm going to take gamma to be non-zero. So let's call them beta plus I gamma. So beta plus or minus I gamma are zeros of S chi with gamma non-zero. So it's not going to fall back into the case where it is real. Yeah, it's zero. In that case, then what can I do? I go back to this business, L prime. Maybe I should have had a minus for this first. Is there a minus here? Should there be a minus? I have to check. Okay. Then minus L prime sigma rho upon L sigma chi. Okay. This is less than C1 log Q minus 2 times sigma minus beta, because rho is equal to, the real part of rho is beta, okay? And this is beta, sigma minus beta square plus gamma square, yeah? Because, okay? Should this be a minus here? Should it? Now, what is this L prime? What is this business L prime? Sigma rho, sigma chi. This is the logarithmic derivative. L sigma chi is. Does this ring a bell? Is this something that you have seen before? Yeah, we saw it. What is it? This? Can you write this, for example, as a Dirichlet series? Yeah. Remember this? Who? Yeah, you can. What can you do to it? Rina? Huh? Gamma. Who is gamma? Fun Mangal gamma. Yes, yes, you can have fun Mongol. Fun. That's not gamma. This is lambda. This is big lambda. Small lambda is this one. Okay. I mean, in tech, it is lambda and lambda. Okay. That's not gamma. It's lambda. Okay. So yes, it is the sum of, you have lambda n, and then, but if you have your chi here, why don't you use your chi? Okay. And then this is it's only with the sigma, therefore you don't have n power s, you have n power sigma, and you let your n go from 1 to infinity. And can you bound this? Can you I don't really have to get exactly any value. Wait, there's a negative here. So this is equal to it, and it's not equal to it. It can be bounded by what? What can this be bounded by? Wait, before bounding it, I will make it equal first. So you see lambda n. So chi n power sigma. Who is this? What is this? This is the derivative of rho of zeta. Yeah, this is equal to zeta prime by zeta for what? Not for this is zeta prime sigma by rho of sigma. And this I know from the second. Yeah. Yeah, so maybe I should straight away make it greater than. Yeah. Yeah. Let me do that. Thank you. So let me do that. I should remove the character first. Yeah, because so this is lambda and sigma n. So this is greater than or equal to. I forget the character. Greater than or equal to lambda n by n power s. There's a negative somewhere, and going from 1 to infinity. Yeah, and now this is zeta prime by zeta, but real. Okay, and that's bounded by, remember what we did right in the beginning, and that was minus 1 by sigma minus 1 minus some constant C0. Okay, for some C0. Okay, therefore what remains now is that I should choose now sigma nicely. So what would you suggest? What would you suggest as for a choice of sigma that would make our lives easy? So if I choose sigma, equal to 1 plus 2 delta upon log Q. Okay. You have seen enough proofs to know that, to not ask, why do I choose this one? We choose one that is convenient to us, all right? Because we anticipate what's going to happen. So we take first some bad sigmas, and then it doesn't work, and then we come back and we get a good sigma. Okay, a good sigma. It doesn't have to be this is not a canonical sigma. Okay, so this minus 1 minus sigma. Okay, yeah. So now I have chosen this. So now gamma, you remember what our gamma was? What was our gamma? This is less than, where is my gamma gone? Here. Gamma is sitting over there. Okay. Okay. Now gamma is less than delta upon log Q. Okay. And delta upon log Q. So, and delta by log Q is half of sigma minus 1, which is less than half of sigma minus beta. So now go back to the inequality that we had in the beginning, and we can write the inequality in terms of minus 1 by sigma minus 1, okay, less than C2 sum log Q minus 2 times sigma minus beta square. What was my inequality? Just a minute. My inequality was sigma minus beta square plus gamma square. Yeah, but we know that gamma is less than delta by log Q. Therefore, gamma square is less than 1/4. This is gamma. Therefore, gamma square is less than 1/4 sigma minus beta square. And if I simplify, I get this one, sigma minus beta square plus gamma square. This is less than sigma minus beta square plus 1/4 sigma minus beta square. So the 4 and the 1 adds up to give me a 5. So this is equal to 5 by 4 sigma minus beta square. All right. So if I have a 5 by 4 in the denominator and a 2 in the numerator, this becomes, I simplify this to make it minus 1, the 5 by 4, the sigma minus beta square cancels with the sigma minus beta in the numerator, and I get minus 1 sigma minus 1 less than C2 log Q minus 8 by 5, the 4 over there, with the 2 comes 8, the 5 is here, sigma minus beta disappears, and I get sigma minus beta square minus 5. So what is the conclusion then? So beta is less than 1 minus sigma by log cube. So what was it that I was trying to prove? I was trying to show you that I could not have 2 zeros. In this particular case, not 2 complex zeros. Have we shown that? Is this, where is the contradiction? Where is the contradiction? The question is, I had I said that I assume that there are two zeros. In this particular case, two complex zeros. And now I have shown all this. I have shown that beta is less than 1 minus delta by log cube for sufficiently small delta. Okay. So where was the problem? Where is the contradiction? We took two zeros and we arrived here. And where is the contradiction then? Can you think about that? Okay. Habibur, what do you think? Yes. Yeah. 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 So the convergence, the question is the question of the convergence, which is not. Okay. So now, okay, another question. If I had taken only 1 0, could I do that? Would this still happen? So as soon as it's true for 2 zeros, well, it's true for more zeros. But what would be the problem with one single zero? Would you be able to come to a contradiction? Would there be a contradiction if we had 1 0? Where did the two zeros play a role? The double zeros. Yes. Yeah. So of course you cannot eliminate this and get no zeros. Yeah. Because then there would be no zeros. Yeah. So that's the proof of this. Okay. I mean, we haven't really done the complete proof. I have done the part where we have done the part which is fundamentally different from Riemann zeta. Yeah, the part one where the complex zeros are, where chi is complex, will be done in an exercise. Okay, it is very similar to the proof for Riemann zeta, which you have not done, but then that is also a way to do the proof of the Riemann zeta. Yeah. However, this part will not come in the other one. Okay. So in fact, we know that an exceptional zero, so these are Ziegel zeros, exceptional zeros, they might exist. Yeah. So there is no proof that Ziegel zeros or Ziegel or exceptional zeros do not exist. So So once they do not, we do not know whether they do exist or not, we try to find other properties for exceptional zeros. Yeah? What other properties can we find for them? So, so several results actually exist of this kind, none of which I will prove in detail because because they are somewhat long, the proofs. And so do you have the books that we recommended? You got the books? So for example, one place where all the theorems are done out in big detail, it's in Montgomery and Vaughan. Okay, but there is a but. Montgomery and Vaughan, if you look at this particular theorem, he does this with explicit constants, and therefore no, it's not a he, it's they. They do this with the explicit constant, therefore the proofs are a little more complicated. Okay, because instead of some delta there, you will find a 6, or you'll find a 35 by 7 or something like that. That. But if you, I mean, you somehow imagine that those are not explicit, and then you can go ahead and see the proofs. Okay, all this part, this is chapter 11 of this book. It's available in the library, you said? Yeah, it's available in the library, and you can check out on the proofs and convince yourself that what we are saying is actually true, even if we haven't done all the details, which in any case is not possible to do in a week. Yeah. So so there are certain things that that we can do. We know that if the exceptional zeros exist, then they are very close to the line real s equal to 1. No, that's not true. They cannot be too close, okay? Exceptional zeros. Oh, I'm not supposed to write with a white chalk, yeah? Exceptional zeros and the line real s equal to 1. So for this, there is a very famous result of Siegel. After whom the zeros are named, yeah, the Siegel zero. But apparently Landau found them before, but never mind. So Siegel, so he proved that if chi, this is result in 1930, so almost 100 years old. If chi is a quadratic character, modulus q, and no, then for all epsilon positive, there exists a constant which depends, which is not absolute. There exists a constant C epsilon, okay, such that L1 chi, so here S is equal to 1, is greater than C epsilon by Q to the power epsilon. Okay. Does this look like a very nice result to you? So I'm saying that L1 chi will be at least as big as some constant upon Q to the power epsilon. So how do you feel about this result? What is your impression of such a result? How do you think this, what kind of, how would you qualify such a result? Do you think it's a useful result? It could be. Yeah, there's something else than the problem. You note that. Yeah, Habibu, do you? Do you know? What's wrong with this theorem? What's wrong? Not doesn't mean what's wrong. The theorem is correct. What I mean is what's not good about this theorem. The constant is ineffective. Okay, so it is a wonderful theorem, but 100 years later, this constant is still ineffective. Do you know what an ineffective constant is? An ineffective constant means that no matter how hard you try, you cannot calculate it. Okay, it's not because your computer isn't good enough. It's because the method is not good enough. Not good enough. The method includes certain things which makes it ineffective. So this is very important. So the important thing is that this is C epsilon is not effective, is non-effective. Yeah, it is non-effective, which means it cannot be calculated. Okay. Okay, so that's a drawback. It's not, there's nothing wrong with the theorem. It's a drawback of the theorem that we don't know, we cannot calculate the C epsilon. So a lot of effort has been made, but as I said, it's 95 years now, and this no effective version of the Ziegel's theorem exists still. Yeah, looks like a very simple theorem, doesn't it? L1 chi is greater than C epsilon upon Q to the power epsilon. So one of the things that in the study of the zeros of L functions is to perhaps find some way to get a more workable result, something with which you could work. This one you cannot work with. You know that it exists, okay, well and good, but we don't know how to find it. Yeah, there is no way to find it, and there will be no way to find it. Yeah, so so that's an open question. Yeah, so so that's an open question. How to get an effective version. Yeah, that's an open question. So whether or not I will prove the Ziegel's theorem, I mean, I will not prove it, Ziegel proved it, but whether or not I will give you the proof is something I haven't decided yet. So I don't really know whether there is an easy, a doable way to present the proof. I need a little time to think about that. Yeah. So if we do not do the proof, at least I will give you the idea of how this is done. Yeah. Then I want to mention some of the other related results to this. So, for example, there is a result of Landau which says that, so there are three results that are quite important in this, classical results that are important. These are results of Landau, of Siegel, Landau-Page, and Esterman. And but if you hear the names, you see that these are very old results. Yeah, these are very old results. There is one result which I said effective result. There's a result by a contemporary mathematician Tatuzawa, but it is not a complete result. It's under certain assumptions. Yeah, and at the end I will give you a conditional result as to when Siegel zeros will not exist, and this will pass through the question of the Goldbach problem. Yeah, it's not an unconditional result. It's a result that will say that if certain things are true, then the Siegel zero does not exist. Yeah, and not the other way around. Not that if the Siegel zero does not exist. Yeah, so yeah, so let me give you a result of Landau. So theorem. So if I take 2 constant positive C such that if chi1 and chi2 are quadratic, modulo, two different moduli are possible, q1 and q2, and if I take the product chi1 times chi2, you know that I can take the product. If this is non-principal, that is, you mustn't choose chi1 and chi2 such that the product becomes principal, then Ls chi1 times Ls chi2 has at most 1 0 such that the 0 is written as beta plus I gamma, 0 beta, such that beta is less than 1 and greater than 1 minus C upon log Q1, Q2. So what does this say? How should you interpret this result? This result says that if I take a product of two L functions, where chi1 and chi2 are quadratic, even if q1 and q2 are different, then the product of the L functions will also have at most 1 0 in this region. For that also you'll be able to find a constant. All right. Now, do you remember that last time, yesterday, we did a theorem which said that L1 chi was not equal to 0. Yeah, the fact that L1 chi is so we can use the fact that L1 chi is not 0, but we can also use the fact that individually, if I take a function Ls chi1 and Ls chi2, each of them can have at most 1 0 in the good region. Yeah. So if so since there is at most 1 0, so again I'm giving you a sketch. Okay. So that means that you cannot have beta 1, beta 2. You have, if there is beta 1 and beta 2, so beta 1 will come from, for example, LS chi 1, okay, and beta 2 will come from so the idea is this proof is not so difficult. Yeah. So since there is at most 1 0 of each of DL functions, you can assume let beta 1 be 0 of LS chi 1 and beta 2 of LS chi 2. Okay. We said that there exists a constant C. We will let this constant to be small. Okay. We can say that if the constant is small, how small? So you can choose not really, yeah. Let beta I be between something, some alpha and 1 for a suitable constant. Now, why can this happen? You see, if C is small, yeah, then beta is between on one side it's less than 1, and on the other side it's you are closing in the gap if C is small. Yeah. So then you can use some result on L prime by on use bounds for L prime by L and zeta prime by zeta, and this should give you a result like that. Yeah. Would you like to try that? Yeah. You can try that yourself, and we can see if you are capable of doing that yourself. And yeah. So do you think we could break now? Because I mean, we can do a little longer in the afternoon. Is that okay for you? If we break now and have a longer session in the afternoon? Is it okay for you? So it's 12:30. No, I mean, if I stop now, then we can go a little longer in the afternoon. And so what is it? Whom is it bad for? No one. Okay. There are some ratios to be, some ratios to be respected. Okay. So Yeah, because now if I start saying something, I have to start saying something that is new. And that's not a very intelligent idea to start something. Yeah. Yeah, but who's going to think about that? Yeah. Okay. So you can think. You're allowed to think. Okay. And then the part of the complex. You see, when we did the first part, the chi being complex, when we did the zero free region, then I said there was one part which was going to be complex. Yeah, okay, I can give you some ideas of how that is done. Yeah. So some hints on that part. Yes. Yeah. Mm-hmm. Yeah. You have to find something else. There is no formula for it. Okay. So it's not an algorithm. Okay. It just happened that it was true for a certain theorem. It's not an algorithm. All right. So, but there is one thing that you should notice, that yeah, here you can assume what you know already. I mean, not assume. You can use what you know. You know Ziegel's. For example, Ziegel's theorem. If you like, you can use that. Okay. So let me let me talk a bit about this. Let me talk a bit about this complex. The zero free regions. Yeah. The part that we left as so complex zeros. Yeah. Not complex zeros. Complex chi. That's the part we left. Okay, so I suggest, okay, that first you prove this. Mod Q. And if sigma is between 5/6 and 2, then L prime by L S chi is equal to E0 chi. I'll tell you what E0 chi is, upon S minus 1 upon some 1 upon S minus rho, where rho runs over all the zeros, and plus an error term O log Q tau. Okay, so for which rho minus 3/2 plus IT is less than equal to 5/6. And what is E0x? E0 chi? E0 chi is equal to 1 or 0, depending on whether chi is equal to chi 0 or chi is different from chi 0. All right. So maybe you can begin by proving this, and then we can continue to the rest. This is a result that you might need. And after that, if you decide to not use it, anyway, you have done this, that we might need for the complex chi's. So can you try to prove this now? We can do that. That can be something that okay. Or if you assume this, this is one thing you can prove. Then another one that you can prove is to prove that if sigma is greater than 1, the real part of this will all help you get the bounds, yeah? Minus 3 L prime by L sigma chi 0. Thus, perhaps you will see why we are doing minus 3, minus 4, and things like that. L prime by L sigma plus IT chi minus L prime by L sigma plus 2IT chi square is greater than or equal to 0. Do you have some idea about, oh, there should be some bracket that closes somewhere? Yeah. So do you have an idea where those 3, 4, and 1 are coming from? These are from trigonometric identities. You remember? Yes? Yeah, exactly. It's because these are things that come from the, for the Riemann zeta, it's you find this logarithm, these cosine functions coming up, and that's where the 3 and the 4 come from, 3, 4, and 1. Yeah. So this is the second thing you can prove. I'll give you some more things to prove so that you don't feel idle. And here, 3, prove that this is the Euler gamma function, gamma z. Prove that this is equal to log z plus big O of 1 by z. When is this true? For this z, which is going to infinity and in a certain angle. And where is that? If the argument of z is between pi minus delta and minus pi plus delta for a fixed delta greater than 0. You can prove this. Yeah. Fourth, It's another question concerning the Euler-Gamma function. These are nice exercises. They help us understand and use certain techniques. You can log of gamma z is equal to z minus half log z minus z plus half log 2 pi plus an integral u minus u plus half. Does this remind you of something? Does this last integral remind you of something? You probably saw something like that for the Riemann zeta. You take the half part out and then you use a contour integration. Yeah. So that's another question you can think about. And yeah. This is the fourth question. Yeah? So you can start thinking about that. Are the people online also solving the problems? Do they solve? Hmm? Oh, okay. Go and wash my hands. So have you, sorry, have you made some progress? Not yet. Okay. You have the definition of Z, gamma Z. So how is it going? Have you made some progress, positive or negative? So shall we meet in the afternoon and I give you some solutions? No, you give me some solutions.